In this video, I'm going to talk about conservation of momentum and how we can use this principle to solve for velocities of objects after a collision or explosion. So let's do a little bit of review. Remember, we have Newton's third law, which explains how two objects exert forces on each other when they interact. Newton's third law usually gets summarized as for every action, there is an equal and opposite reaction. So that means when two objects interact, the magnitude of the force or the size of the force on the first object will be the same as the size of the force on the second object, but the direction of the force will be opposite. And then the effect of the force is all going to depend on the mass, because acceleration is caused by the reaction of mass, interaction of mass and force, and so how much an object accelerates depends very much on how much mass that object contains. Newton's third law then is dependent on Newton's second law, which is written that force equals mass times acceleration, or you can arrange that to be acceleration equal to force divided by mass. To visualize Newton's third law, we can imagine two people on roller skates, because roller skates will help decrease the friction, and they are of different masses, but they're going to push against each other with different forces. So the forces are equal but opposite in direction, and then the resulting the effect of that force is going to cause both of them to accelerate away from each other, but because the masses are different, our end velocities caused by that acceleration will also be different. Even though we may conceptualize this as one person able to push harder than the other, it is not the case. The force is exactly the same as these two objects interact, but the end result will be different because of mass. Since collisions are definitely interactions of two objects or more, they are controlled by Newton's laws. When a collision occurs in an isolated system, and I'll talk about that in a minute, then the total momentum of the two objects before the collision will be the same amount, equal to the total momentum of the two objects after the collision. Again, the forces are equal and opposite. The time of the collision would be equal for both objects. And because of that, force and time together makes impulse. So the impulses will be equal, but opposite in direction. And then the changes in momentum will be equal and opposite in direction. The end result is something we call the conservation of momentum. The total momentum of the system is conserved. It does not change. It does not go away. So let's think about a collision and put some numbers on it. Let's suppose that we have a train car that is going down the track, and its mass is 42,000 kilograms, and it's traveling at 10 meters per second. So we know that the momentum is going to equal the mass times the velocity. And so our momentum will be our mass, 42,000 kilograms, times our velocity of 10 meters per second, which gives us a total momentum of 420,000 kilograms times meters per second. With that strange unit, remember, that happens when we multiply these units together for momentum. So that's the momentum of this first train car. The second train car is sitting there on the track, and so it's going nowhere. And without motion, you don't have momentum. So we have zero momentum present. So we'll say this is train car 1. And so the momentum of train car 2 equals 0. So the total momentum of the system will be 420,000 kilograms times meters per second. They collide together, they get hooked together, and then they continue. The force of the moving car on the stationary car is going to force that stationary car into motion. So now we have a system of two train cars moving together at a velocity of 6 meters per second. So that will give us a total velocity of 6. But we don't know and we know the mass of the first car, but we don't know the mass of the second car. But we can figure that out using, again, our same momentum formula. So we know our starting momentum. The momentum of that first moving train car was 420,000 kilograms per meter times meters per second. I'm just going to drop units just for space purposes. So that momentum is going to be carried, or is going to be passed on to these two train cars moving together. The mass of the train cars then will be equal to 42,000 of the first car plus an unknown mass of the second car, with the whole unit together then moving at 6 meters per second. And now we're basically left with a math problem where we're trying to isolate what m equals. So we're going to have to divide both sides by 6, and that will give us 70,000 over here on the left, equal to 42,000 plus our mass, and then we subtract 42,000 from both sides, and that's going to tell us how much our mass of our tanker car is, got collided into on the track, which is 28,000 kilograms. So our momentum equation can be used to determine mass or velocity in a collision. If we are able to then figure out the starting momentum, we can use the conservation of momentum as the principle for figuring out that missing variable. So isolated systems, as I said, this works in isolated systems, that momentum is conserved between objects. And in an isolated system, there's no other external force that's going to alter the momentum of the system. The only forces involved are ones that are coming from the forces acting between the two objects during their interaction as either a collision or an explosion. While we do have friction and air resistance present as objects interact kind of out in the real world, often the forces that they can apply to objects are really so small that they don't really affect momentum. And so they might make a 1 or a 2% difference. And so we're just going to ignore them. Instead, we will use conservation of momentum as the rule for determining or predicting pre- and post-conversion speeds or sometimes masses. So let's do some examples here. So we have a weighted ball, a medicine ball, that is thrown at a velocity of 20 kilometers per hour to a person that weighs 60 kilograms, and it is at rest on ice. So with friction, again, we're minimizing by putting them on skates. The person catches the ball, so the force of the ball coming in is going to accelerate this skater and ball combination in a backward direction. And so after the person catches the ball, they're going to be sliding across the ice. We can use conservation of momentum to determine the velocity of the person and the ball after the collision. To do that, we set up something called a momentum table, where we compare what's happening before the collision and after the collision, and fill in basically the missing pieces, because we know that our total momentum in both cases needs to be equal. So the person before the collision is going to have no momentum. So this is momentum this is a momentum table. So we're thinking about momentum. We're thinking about that. The momentum is going to equal the mass times the velocity. This person has mass, but they don't have velocity, so they have no momentum. The medicine ball has a mass of 15 kilograms, and it's thrown at 20 kilometers per hour. So we can multiply the mass times the velocity to get a momentum of 300 kilograms times kilometers per hour. Remember that often our unit for velocity is meters per second, but not always. So then with momentum problems, sometimes the velocity is going to be in unusual units or less common units than meters per second, like in this case, kilometers per hour. So anyway, our total velocity for the system before the collision is 300 kilograms times kilometers per hour. After the collision, we have the person is going to have their same mass of 60 kilograms times an unknown velocity to give their momentum, and the ball is going to have its mass of 15 kilograms times an unknown velocity. But together they're going to equal that 300 kilograms times kilometers per hour. I'm getting confused with so many kilograms. And so because this is a multiplication, it's times velocity, we'll be writing 5x. You just can get rid of that 5 sign, and you're going to have 60v plus 15v, giving you 75v equals 300. So we're just doing algebra here. And so you'll be dividing both sides by 75. which gives you a final velocity of 4 kilometers per hour as the velocity of this total system going together, because the momentum has to be equal to the velocity and masses of everything involved in that collision. And so we're able to use our momentum equation and basic algebra to figure out how fast they are moving. This type of collision is called an inelastic collision because the objects stick together. There's no bouncing going on. Now, of course, objects don't always stick together when they collide. Sometimes they will bounce off each other. Sometimes they will basically transfer a little bit of velocity and then separate. And so these are known as elastic collisions. And here's an example where we still can use the same momentum table to figure things out. So we have a truck that weighs 3,000 kilograms and it's moving at a velocity of 10 meters per second. It runs into a parked car that's just sitting there not any momentum because it's not moving. And as a result, the car is pushed forward after the collision at 15 meters per second. But the truck now has changed its velocity, and we're going to try to figure that out using the principle of conservation of momentum. So again, we think about what's the situation before and what's the situation after. Before, the momentum of the truck is the mass, 3,000 kilograms, times the velocity, 10 meters per second, giving us 30,000 kilograms per meters per second. The car is not moving, so it has no momentum. So the momentum of the system before the collision, which will be the same as after the collision, is 30,000 kilograms times, I wrote kilometers per hour based on the other problem. Sorry, this should be meters per second. So then what happens after the collision? Well, our truck has changed its velocity, but it hasn't changed its mass. So we've still got that 3,000 kilograms times this unknown velocity. We know that the car weighs 1,000 kilograms, and we know its velocity of 15 meters per second. So we know there is 15,000 units of momentum going on with the car. And basically, we have our unknown units of momentum from the truck plus our known units of momentum from the car equaling 30,000. And again, we just would apply algebra. We would subtract 15,000 from both sides and then divide by 3,000, which gives us an answer of 5 meters per second as the velocity of the truck. So some of the velocity, we've lost velocity as the truck has gone from 10 down to 5 because it has collided with the car, and some of the velocity that it had been carrying has been transferred over to the car. The momentum that it's been carrying is transferred over to the car because the car is now in motion. Now we know the equation for figuring momentum is mass times velocity, which means the relationship between mass and velocity is an inverse one. If mass goes up in a system, then velocity has to go down in order to get the same number for momentum. If we're going to double the mass, we'll cut the velocity in half. If we cut the mass in half, we will double the velocity as a result. It's an inverse relationship. You can imagine this by a situation where someone is an astronaut and floating in space, and so they're collided. Another astronaut collides with them, and if the astronauts weigh basically the same amount of mass, then you go from a momentum of this one mass times a velocity becomes a 2 mass times a velocity situation. And in order for the end results, in order for the momentum to stay the same number, the velocity would have to be cut in half. So if our velocity is 1 over here, it would be 1 times 1 equals 1. And so it would have to be 2 times 1/2 to equal 1. So that's that inverse relationship being shown between mass and velocity because of conservation of momentum. In an explosion, you have an internal impulse that's propelling the various parts of the system into a variety of directions. After the explosion, then, all of these individual parts of the system have momentum, and the momentum, if you add them all together, the overall momentum of the system is going to be the same after the explosion. So it's it's not a collision, but the same principles of conservation momentum still apply. Evidently, exploding watermelons are a thing because there's all kinds of pictures of them on the web. So we're going to be just sort of, how do we apply then the conservation of momentum and thinking about what's happening to the parts of a system that are heading off because of an explosion. So let's imagine you have a 56.2 gram tennis ball, which is loaded into a homemade cannon, and the cannon is ignited to send the tennis ball, flying through, hopefully outdoors. Let's not do this indoors. You have fancy equipment, so you can record that the cannon's going to recoil backwards. After the explosion, it's going to travel a distance of 6.1 centimeters in 0.0218 seconds. And you can use this information to determine the post-explosion speed, or the velocity, of the cannon and of the tennis ball. Now, we know the speed of the cannon because we have both a distance measurement and a time measurement. So remember, our speed is going to equal distance divided by time. So that would be 6.1 centimeters divided by 0.0218 seconds. And if we do that math and round it off, that's going to give us a speed of 280 centimeters per second. And since we're dealing with velocity here, that's speed, of course, but we're dealing with velocity and it's sending the cannon backwards, it is a negative value. And so then using our momentum table again, we think about, well, before the explosion, the cannon and the tennis ball are basically at rest. So there's no momentum going on. So our total momentum of the system before the explosion will be 0. But after the explosion, things are moving. The total momentum still has to equal 0. What's happening? We know that our cannon weighs 1.27 kilograms. We have figured out its speed as being a negative 280 centimeters per second. Now, what about the tennis ball? The tennis ball's mass is given in grams. We've got to do a conversion. So remember, our King Henry died by drinking chocolate milk. Gram is the base unit in the middle. In order to go from grams to kilograms, we're moving that decimal point 3 places to the left. So he started here at the 56.2. It's moving 3 places to the left to giving us 0.0562 kilograms. That'll be times the velocity that we're trying to figure out, our unknown speed of the tennis ball. But all of that still has to equal 0. So now we just need to do some math. So what's 1.27 times negative 280? If you go ahead and do that math, that's going to be a negative 355, and that'll be kilograms times centimeters per second. I'm just going to drop the units. So we know that momentum, the momentum of the cannon, plus the momentum of the tennis ball, which we haven't got all the information on it yet. We know it's 0.0562 v because we have to figure out the velocity. That all is going to equal 0. So how are we going to solve for v? Well, we've got to add 355 to both sides. And then we'll go through and divide by 0.0562. Again, this is just applying those basic algebra techniques for isolating v. So if you do the math, you're going to discover that v equals 6323 centimeters per second. Or if you go ahead again from centimeters to meters, we need to move our decimal point 2 places. To go from centimeters to meters, we'll move it 2 places to the left. So it'll give us a velocity in more commonly used terms of 63.2 meters per second. So again, this momentum table where you're thinking about the momentum before and after applies for collisions and explosions. It's just a handy way to kind of organize your thinking between that and your momentum equation of momentum equaling mass times velocity and some basic algebra. You're good to go to figure out these problems. So just thinking about, check for understanding. Can you explain how Newton's third law and second law are seen in the momentum changes that are experienced in collisions and explosions? Can you explain what conservation of momentum means? Can you explain how increasing the mass of a collision requires a decrease in velocity? And can you use a momentum table to do these various calculations to compare pre-collision or explosion momentum to post-collision or explosion and determine velocity or sometimes maybe even mass, depending upon what variable is missing?